Welcome to the Australian Water School, the home of demand-driven industry design training for the global water sector.
Welcome to today's first Two-Flow webinar for 2022. We are absolutely delighted to have you with us. Thank you for joining. We've got the best minds at work on this one, Bill and Chris from Two-Flow and their colleagues, Phil and Greg. We would love you to get your questions and answers ready for this webinar, your comments, anything that you want to add to the discussion will make so much difference. Thanks so much. Look at that map. This is what I want to get to today. It's wonderful to see so many joining us today, 1,000 plus, around 1,000 registrants across 50 plus countries. You can see it on the screen there right now in front of you. So good to have you all join us. Thank you so much for taking the time on this. It's going to be fantastic. You won't regret this, I'm dead sure. Bill, Chris, Phil, come on screen. Let's have a chat and get this thing underway. Bill and Chris, Phil and Greg are the brains trust for Two-Flow. Am I going over the top here? Sorry if I am. Let me know, Bill, what you think there. But these guys have been thinking about hydraulics, hydrology, and how to model it for many years. Wouldn't like to say how many, Bill?
Too many.
You've lost all the hair on your head. I mean, this is really hair-tearing stuff.
30 plus years, but I don't come close to Greg when it comes to this stuff. So yeah.
Oh, well said. Well said. Greg, hold the fort, and Chris and Phil, you were spread across Australia, ready to go with this webinar. Thanks so much, you guys. It's so wonderful to have you guys taking this time today. And thank you everyone for doing this poll at the front. Gives us a bit of a clear idea. Any comments on this one here? Commercial consulting, you can see in the screens there, is obviously the top winner there.
Yes,
down we go. Yep.
A lot in consulting, and I mean the last one is always of interest. So yeah, no, we've obviously got some pretty key modelers out there in this space. Yep,
and 5+ years, lots and lots of them there. Often undertake pipe network modeling. Fantastic. Thanks everybody for that. That helps us just hear this this webinar a little better, and our future webinars as well. Thanks for that survey there. Now, how we're going to do this is Bill's going to kick it off, and then Chris, and then throughout the whole of the webinar, Greg and Phil, you're ready to roll with questions and answers. And I'm saying ask Phil and Greg the hard and awkward questions. And if it gets too awkward, they'll have to come on screen and do a rant with Bill and Chris, maybe. No, do that. That'll be wonderful. It'll help us, help the discussion go ahead brilliantly. I've enjoyed working with these guys for years, and you will too as we get going here. That done, over to Bill, then you'll hand straight to Chris. Thank you.
Yeah, thanks, Trevor. Thanks to Australian Water School. These guys do a fantastic job, and it's actually it's fantastic to be back for another year of webinars. So we've got quite a lot lined up. So hopefully you'll enjoy them. Yeah. So the basic focus for today is on pipe network modeling, but really around modeling urban inundation. And what we're talking about there is where we have our pipe network underground, but there's also overground inundation, which may be part of the design, may not be. In this case, it's contained in the road. But obviously at times it gets up to house levels, which is undesirable. So today's discussion is around that space. The first half, I'm going to dive into a bit of theory on some more probably challenging or interesting aspects of pipe network modeling in this space. And Chris is going to take over around halfway to look at practical and quality control aspects of, particularly when you get into very large networks where you really got to be on top of your data and etc., which is hard to do when you've got a lot of data. So let's dive into the theory. Today, what I'm going to cover briefly is the different pipe flow regimes, just to get our minds thinking about what sort of flow you can have in pipes. A large part of my presentation will focus around energy losses, particularly in manholes, because that's probably the hardest thing hydraulically to deal with, which I'll explain. And then I'll briefly just run through some of the other aspects that you come across in this type of modeling, such as overland flow capture, surcharging, blockages, and operational structures. A bit of terminology. Most of you will be familiar with this terminology, V for velocity. So I'll talk about the inflow or inlet pipe velocity. So this is the velocity of the water flowing into a manhole and velocity out, VO. Hydraulic grade line is commonly used, and the way to interpret what the hydraulic grade line is effectively the water level. But when your pipe is flowing full, you have to imagine it as the water level if you stuck a vertical tube into the top of the pipe. It's not the total energy, which is water level plus V squared on 2G. And something we'll talk about quite a lot is the energy loss coefficient, which in this presentation I've used K, but other symbols like C are used. And what we're talking about there is the loss of kinetic energy, which you would all hopefully know as being V squared on 2G, which is the difference between your water level and the amount of energy the water has to keep moving itself downstream. Some pipe flow regimes, just on this, it's really about whether your pipe is outlet controlled or inlet controlled. So it has a big bearing on how you establish the flow and the energy losses around your pipe network. So outlet control occurs where you effectively have a tail, a submerged outlet. By and large, it nearly always. What is key is that the flow is subcritical, and some people use the term pressurized. Well, the water level, of course, could be below here, but importantly, it mustn't be going below the critical depth or around that point. So that's outlet control mode in terms of those two outlet scenarios. And in those cases, both inlet and outlet energy losses of that pipe will be important, as well as friction losses along the pipe. There is one other mode, and that is when you have free outflow. And so in this case, the flow is actually subcritical approaching the outlet, and the water transitions through critical depth. And so that will also be outlet control, because the control is at this point here where it goes through critical flow. What's important to note here is the exit loss that you would all be familiar with. Doesn't really apply in this case. It's just the inlet loss and, of course, friction. Inlet control flow occurs where basically you might have supercritical flow, or the pipe is sufficiently steep to generate supercritical flow, and so would transition through the critical flow point. Also, sometimes when you have orifice flow that's not drowned out, you can obviously, the orifice flow forces critical flow regime inside the entrance, and that would also be an inlet control regime. So the typical scenarios are when you have the outlet unsubmerged. So this is just going into supercritical mode. It may or may not be supercritical at the entrance. You could also have the outlet submerged, but because there's a hydraulic jump forming inside the pipe, in other words, this is critical flow, the control is actually at the entrance, not at the outlet. And then you have the scenarios where you have the inlet submerged, you have orifice flow generated and supercritical flow. Once again, you could also have that same arrangement with hydraulic jump forming down. So these types of flows don't occur as often, typically, but they can, of course, in steep environments. What's important to note in this space is that the downstream conditions have no effect on the flow rate. And entrance and exit energy losses aren't used in the computations. So just touch briefly on the one that you would all love and know, Manning's equation. So basically is the loss of energy due to friction, the change in energy or change in water level is a function of the friction slope times the length of the pipe. This is the Manning's equation rearranged in different formats here. I won't really go into details, but what's important to sort of note when you're in pipe world is when the pipe's flowing full, it's actually a really standard, straightforward calculation, because the radius reduces to the hydraulic radius reduces to the radius of the pipe on 2. So it's very, very straightforward. There's no sort of complications with determining the friction contribution to losses. And you can see that in that sort of diagram there. When everything's flowing full, you just have the friction loss plus any entrance exit losses. The more challenging one is when the pipe is partially full. That's an open channel flow problem. It's not straightforward because you can't just simply, everything is dependent on either side, and you have to, basically revert to some sort of open channel solution, which becomes a bit complicated if your pipe element is quite long because your velocity down the pipe will change as your water, in this case, the water level is slowly rising inside the pipe. In this case, the water level is slowly dropping because you've got a free outflow. So it's not a straightforward calculation. In terms of Manning's end values, as you would all know, no doubt there's plenty of guidance in the literature. Pipes will vary. And really all I want to say in this regard is if you're using Manning's end values outside industry guidelines and something is wrong, you have to have a very good justification to do that. And if you're calibrating a model, always stay within the guidelines and look elsewhere for why you might have a poor calibration. So what I really want to focus is on the kinetic energy losses associated with, basically manholes and a sort of simpler version will be a junction where there's no manhole. And bends and obstructions are sort of fall in the same category. But what I'll focus on is manholes. And besides the Manning's equation, this is the other equation that we all as modelers should really have in our heads when we're looking at our results. And that's, really don't have to worry about the full-blown shallow water equations in a way. You really have to just look at where your model is losing energy. And so it can lose energy in two ways, friction, which I just explained before. But when you come to this situation where your water is being forced to change direction in different ways, you have a kinetic energy loss, and this is always a fraction of the velocity squared on 2g, and we use k to describe that fraction. So the most common element, if you like, in your pipe network model that loses energy in this manner is your manholes, but it's also the most hydraulically complex, as I'll explain. But first, we have to think about why we have manholes. From a modeling point of view, it would be much, much easier if we didn't have manholes. Our life would be a lot easier. But they are needed, and they're needed for very practical reasons, such as during construction or if you need to maintain the pipe network. They often are used to accommodate a transition if you're going from a small pipe to a large pipe, where you've got a pipe coming in the side. And they often are the point at which you receive water from above ground inlets. So they're very, very important in the pipe network modeling space, but they're really challenging to model. So let's just look at what is going on inside a manhole. So it's all about the kinetic energy losses around and through the manhole. So here we have a circular manhole, incoming pipe, outgoing pipe, some streamlines, so the water will come out, it will expand. And it's that expansion of water out through here that is where you get your energy losses. So what water hates, water is very happy to contract. It's a little bit, but it really hates slowing down. And the way you have to think about it is, an analogy is that it's quite easy for us if we jump out of something or whatever to speed up, but it's pretty brutal if we come to a grinding halt. So same with water. As water slows down, it's pushing against the water in front, and so it has to dispense energy as part of that process. And it's when the water slows down or is forced to change in a different direction that you lose that energy. And that's what it's all about. So obviously here, the water's coming into the manhole, it's going to expand, you're going to have circulations generated, and it's going to be energy lost. The other side of the coin is when the water recontracts back into the outlet pipe, you'll form a constriction here, which we call the vena contracta, and you'll have a high velocity there. Then that water has to re-expand downstream of that vena contracta, and that will involve more energy losses. So the other thing to just quickly note is these energy losses are really only occurring or are important in our modeling is when the pipe is out in outlet controlled flow regime. Just looking at there's other types of energy losses that can occur in a manhole, just touch on these. So if there's a change in horizontal alignment, so if you have a pipe coming in at a different angle to your outlet pipe, you will basically, it's not ideal because this water has been pushed across to the side here. It's been forced to do something much more nasty than what it would be if it was in a straight line, and you'll get greater energy loss due to the more intense turbulence around there. So a change in your horizontal alignment of your pipes, or if you have two pipes coming in together, will certainly create additional kinetic energy losses. Also changing vertical alignment. So here we have a pipe coming in, it's dropping down and then going out. And that will also create additional turbulence than what you would get if that pipe was in line with the outlet pipe. And you can have other effects. For example, if there's a large amount of water coming in, either from curb inlets or some other way, that can obviously affect the amount of turbulence that you are getting inside your chamber. Okay, let's look at let's do a bit of theory. So just as a bit of a reminder, this is our manhole. Flows coming in, circulating, it's expanding. And so we're going to have losses due to expansion of that flow. So the inlet velocity will be quite a bit higher than the velocity in the manhole. And that, obviously, the manhole is just highly turbulent. But at some point, it sort of reaches a minimum velocity, then it recontracts. And as I said before, it'll recontract. This is your velocity in your vena contractor, which would be the highest velocity. It'll re-expand. And then you get more losses in this space here as that water re-expands. And so these losses are very much dependent on the shape of the chamber and the outlet entrance treatment. So that's the outlet entrance treatment is what you do around this point here, because if that's nice and if that's smoother, you will create a smaller velocity in the vena contractor, because the vena contractor will be larger. This little eddy here will be much smaller, and separation will be less. So there's a couple of ways we can go about modeling these. The two most common ways is to just provide a energy loss coefficient, K, and it's just fixed for the whole simulation, or if you're doing a steady state type analysis, then it's fine, it's just one K value. And so these are, these K values from manhole configuration are derived from either desktop calculations or actually from measurements in flume or possibly the field. And if K varies with flow, in other words, if the energy loss changes with from low flow to high flow, then it's not really ideal to use this approach, but it may be the approach that's preferred. But if K stays fairly constant throughout the course of the event that you're modeling, then it's fine. There's plenty of values in the literature for different manhole configurations. I think the only thing just be wary of is when you see a K value quoted, just be aware of what velocity it applies to. By and large, a K value for the whole K value for a manhole, the total K, will be based on and adjusted to meet the outlet velocity V0. The other approach is to vary your K according to the flow conditions. And so that approach uses equations for the different loss components. And your model is actually recalculating those components every time step to adjust the K according to the flow conditions. And that's quite a nice approach, particularly for dynamic models, which are modeling quite a large range of flows. Okay, so let's look at the fixed K approach. The objective here is that we come up with 1K for this whole manhole. So essentially we're lumping all these losses that we've been talking about as 1K value. And the loss will be expressed, typically it's expressed as a function of the outlet velocity. So that's the velocity down here. So let's assume that that we only have inlet and outlet losses in this case. We don't have any sort of alignment issues. This pipe here is pretty well nicely aligned with this pipe here. And I won't dive into these equations too much, but basically you can derive this equation here is the energy loss due to expansion of water. And the way to think about it is, you might notice if your velocity downstream is zero, such as if the water is discharging into the ocean or a lake, you'll lose your complete kinetic energy because the water is going from, say, 4 meters per second to zero. So you will actually lose that complete V squared on 2G. But as in these situations here, the water doesn't lose all its force. And so the energy loss is going to be a fraction of that V squared on 2G of the upstream one. So that equation can be derived from first principles, and it's commonly used in modeling. So let's just look at, let's do a few calcs. I won't, you can go through this slide later if you really want to. So we have here the inlet loss is based on the velocity here and the velocity here. And if you plug that into that equation, you end up with a K value of 0.56 on VI squared on 2G. So 0.56 times 16 on 2G. In terms of the outlet loss, it's a similar sort of exercise, but we're going from the vena contractor to here. So if we just assume that there's about a 20% contraction here, that will give a velocity of around 3.1 because it's related to the area. So we're going from 3.1 squared to 2 squared. So let's base the energy, the K value, on the outlet velocity, 2 meters per second. To do that, we have to look at the total energy loss, which is the sum of those two here. So the sum of the energy lost due to expanding in the chamber, and the sum of the energy expanding downstream. So that effectively gives us 0.56 VI squared on V naught squared plus 0.13. And you can rearrange that for that. These flow conditions, you end up with a K value of 2.4. And so the really important thing to note here is that K value seems very large, but it's large because it has to be adjusted to work for the outlet velocity. And this is a common thing that's done for developing these K values. So it's not unusual to have K values that exceed 1, and that is because they've been adjusted, the losses have been adjusted to entirely work for the outlet velocity conditions. So that's sort of how you might come around developing a K value, a fixed K value for a manhole with those sort of flow conditions. In terms of the variable energy loss approach, the approach is we effectively take the individual losses at all the various locations, so the expansion here, the expansion here, we add them together. And these are sort of equations that we use. So for this, from here to here, for basically the inflow loss to the manhole, it's using that equation we just talked about before. The tricky thing here is what is the velocity in the manhole that you should use. So there is a fair bit of uncertainty around that. The conservative approach will be to use a velocity based on the full width of the manhole. But sometimes it may be very justified to use a smaller width, and that would give a larger velocity, and that would give less losses. On the exit, it gets a bit more challenging in the sense that we really want to know the loss from here to here, and we actually don't really know what this contraction is, and it doesn't give us a nice exact solution. So what the industry or what models tend to do is that they use experimental data, and there's a couple of equations which are used, and it's based on the manhole upstream velocity and the downstream velocity. So this being a contracted velocity doesn't come into the equation. So that's typically what's done for your inflow losses and your outflow losses. This approach that we use also has an allowance in there for unaligned pipes. So here we have pipes coming in at different angles. That's obviously going to create greater energy losses. And there's an equation here based on the England method, which gives you that. And it might also be a change in pipe elevation. So this variable energy loss approach is using various loss components, adding them together, and giving a total K value, but it's recomputing those every time step to give you changing cave, changing conditions. Just a few things, minimizing energy losses in manholes. So the objective really to minimize your energy losses is to maintain your velocity through the manhole. So obviously keeping the chamber size to a minimum is a good idea. And the other thing that you can do is minimize turbulence and eddies. So, you know, one thing you can do is direct these pipes so that they hit, the flow from these pipes is targeting the outlet point. So that could be something that gives a more, it maintains the velocities or inertia of the water through the system. So that will give you less losses. Benching is used. This is particularly at lower flows. So that's where you bury the pipe into the bed of the manhole. And so basically for flows that, you know, predominantly in this level of space, that will maintain a velocity through the system as well. You can also minimize the vena contracta, the expansion of the water in the outlet, the losses associated with that. So one example is using something like a curved entrance, a bell mouth outlet pipe entrance. And what that does, of course, is that will minimize this, the amount of contraction. Well, actually keep this as big as you can and minimize the size of the eddies and the separation. And that will reduce your vena contracta velocity, and that will therefore produce less losses. So there's a range of things you can do to make these manholes more efficient. I'll just go through just a few other things. I'll go through these slides fairly quickly. They're not so challenging theoretically, but they are aspects of pipe network modeling we need to consider. So above ground flow capture, that's your inlets, pitch drains, gully traps. There's, I guess, quite a lot of approaches to how we deal with these, and they may also backflow or surcharge. So you get lots of weird and wonderful designs in terms of how to capture water from above ground. The other thing you'll notice, or even, you know, we call these things lots of different terminologies. So, you know, we have lots of names for these things, so which makes it a bit confusing at times. The key thing, though, is that basically there's two types of inlet, or in the industry, certainly here in Australia, there's two approaches. There's the on-grade inlets, and these ones are in a situation where you can get a reasonable amount of bypass flow. So the water comes down the gutter, and then it's bypassing. So the inlet, the pit, doesn't capture all the flow. And so there are often approach flow versus capture flow curves for these types of pits. And they can also be converted to a depth versus flow curve as well. Often the relationship, these curves are derived based on flume tests and measurements. These are out of the University of South Australia. But what's also really important, and we're not going to go into this in any detail today, but it's really important that the above ground depths or approach flow is well represented, because particularly most of these models these days are linking to a 2D domain above ground. So it's really, really important that the depth feeding into these pits, into these inlets, is accurate. So sag inlets are the other type of inlets, and these tend to be where you have water ponding at the end of the drain, maybe, or something like that. And so water is basically being captured, and this tends to be very low velocities around these. So it's quite a different loss mechanism. There's no bypassing assumed in the curves. And the other thing to be considerate of is that these are very good at collecting debris. And I'll mention blockages in a second. And these pits or inlets, they can also backflow, they can surcharge. So your modeling has to be able to handle that, and there's different ways of doing that. So very important that when your pipe capacity gets exceeded, the water can, reverse, if you like, back up and out through the system. And the reason that might happen, of course, is you could have blockages in the system, in the pipe network. You might have a river in flood, which is not allowing the pipe network to discharge. So there's lots of reasons why this happens. So it can be quite important to be able to model this effect. You may even need a different depth discharge curve to do that. And it's also just be conscious that sometimes the actual water level on the ground will actually control. It's basically be downstream controlled in terms of the amount of water that come out through the surcharging. And the other thing that can happen, of course, is your manhole lid can pop, and that can cause a lot of sudden backflow and cause all sorts of problems. Probably what I wouldn't recommend though is doing what this guy's about to do, and he quite brave and stood on that. But good thing that I wouldn't recommend that when you see what can happen in something like that. Blockages, huge issue, typically a really, really big issue. And in Australia, there's lots of strong guidelines around that, and no doubt in other jurisdictions there is as well. But blockage can have a major impact on how your water gets into your pipe network system, and of course, even internally inside the system. This is one of my favorite photos. So this bridge here, the rails on this bridge were specified because they're not prone to collecting debris. Anyway, so it can happen. Just to finish up, for my side of things, operational structures, I'm not going to go into those, but they often occur in these pipe network modeling. So you may need to be able to model backflow devices, and they can have very specific energy losses associated with them. Pumps and gates and other things like that. But we have a webinar coming up in April 13th, where we will be diving much more deeply into operational structure modeling. So that's all I had to cover, and I'll now hand over to Chris.
Okay, yeah, thanks for that, Bill. That's all the theory. Based on the feedback we've received from previous webinars, there's a call for some more practical examples. So I thought rather than continuing on with the theory, I'd provide some demonstrations, basically, how to quality check the data that goes into your models. This is particularly important with pipe network models because you're often dealing with very large data sets. This example here, this is a catchment down in Melbourne. This is actually what triggered the tool that I'll be presenting later on. It included over 10,000 pipes, inlets, manholes, very, very big data set. And it was of varying quality. There was lots of issues with the data. There was connectivity issues. That's where, in reality, the pipe network is all connected, but in the digital data set, it's not. Alternatively, there was also object direction issues where the inverts of the pipe suggest it should be flying one way, but it was digitized the other way, which would have actually caused things to back up. And there was just errors, errors in the data. Here's a long section. You can see there's one pipe which is digitized in the wrong direction. There's another pipe that is quite possibly not real, that small one there. In some other locations, there was areas where the pipe inverts were listed as being well above the ground level, which doesn't reflect reality at all. And with all modeling, when we're talking about modeling outcomes, the quality of the data that goes into your model has a direct impact on the quality of the results that you get out of it. So with that in mind, it's very important that you quality check your pipe network data before you even start your modeling. I'll be doing that using QGIS. I'll be using the 2Flow plugin. I assume that everyone is probably using QGIS, but with 1,000 registrations for this, even if 10% of you aren't, I'll go through the basics so you're at least familiar with it. Okay, so to install a plugin, just click on the plugins tab and go and scroll down to manage and install plugins. If you're looking for the 2Flow plugin, which I'll be using, search for it and click install. It's as simple as that. After you do install the plugin, you'll see there's a variety of different features included in the 2Flow plugin, and one of them is the 1D integrity tool. That's what I'll be focusing on now. And there'll be 4 specific functions I'll provide a demonstration to. That's the snapping function, pipe direction, check function, network continuity, and also flow trace. The prior data set's probably a bit big for a demonstration, so I've pulled this down to a smaller model. This one here only has about 1,000 pipes. It uses a 2D cell resolution of 1 metre per cell. And we've used a direct rainfall inflow approach. That's where every single 2D cell gets wet and then the water flows over, and where you've got inlets, it goes into the pipe network. Let's start by looking at the snapping tool. First of all, I'll just open up the 1D integrity tool and I'll load in the input data sets. When you do load the integrity tool, you'll see there's 2 different blocks to the interface. There's an input layers block and then also the functions block. In the input layers section, you can actually load in multiple different data sets. If your pipe network data is made up collectively of, say, 10 different data sets, you can load them all in at once and it'll assume they're all together for these subsequent analysis. So we'd load those files in. And then once they're loaded, it's just simply a matter of going down to the function that you want to use and clicking run. Here I'll start with using the snapping tool. It's essentially looking for any locations in this pipe network where the features are not snapped together within a defined exclusion radius. So within 10 map units in this instance. And it's identified around a dozen locations where it thinks there might well be pipes that should be connected that aren't. If we zoom in on one of these locations and just look at the input data set, things look like they line up, but zooming right in, they're not. By default, 2Flow has a 1 millimeter snapping tolerance. So if that distance is less than 1 millimeter, it would assume it was snapped. If it was greater, it would think these pipes are not connected and would cause drama in the modeling. There's a secondary option with this tool called the auto snap option, and I'll use that now, where if I rerun the tool, in addition to creating the output files, which provide a summary of what it's done, it'll also correct snapping issues for you for all of those identified locations. So you can either make this update manually, use the automated approach, or alternatively, I guess, a combination of the two. So step 1, so you create that snapped data set. I would then usually import that data set for the next round of tests, which will focus on pipe directions. The utility includes 2 different calculation methods for pipe direction. I'll just give a demonstration of one. It's simply a matter of loading in the data and pressing run, and it'll produce a report of all the locations where there's issues. And it'll also correct the data for you, so you can then use that in your modeling. It is worthwhile noting that in terms of the hydraulic calculations that Bill was describing, the losses at the manholes are calculated based on the flow characteristics, not so much the direction of the pipe. So if the inverts were correct for that pipe direction, things would still work properly. You'd just find that the flow would be a negative value for one of the channels. That being said, it's much neater and nicer just to have everything consistent. So I'd strongly recommend fixing up these directions if they come up, if they're identified. So there you can see that pipe was digitized in the wrong direction. It was facing left to right. Run this tool and it's switched it around from right to left for me. The next tool is the continuity tool. This one includes a variety of different checks. There's checks for flow area, for invert checks, so it can look for adverse gradients in different parts of the network. Angle check, you'll recall that Bill mentioned that the angle of the pipe does influence the losses. So if the realistic angle isn't used, then that will cause extra losses or less, depending which way it goes. It can also check for ground cover. So we can load in the digital elevation model and just check that all the inverts for the pipe network are in actual fact below ground. So we'll run that tool. I'll just check for the flow area and also the ground cover. Also load in the DM data set. I didn't do that previously. It's very quick to run these, far quicker than it would take to initialize a model. Let me now just turn off the pipe data and then we can look at the output file that will highlight all the different locations where it's suspected there's an issue that you'd want to go and investigate to confirm whether the digital data you have is real or not. Here we've got, what, 24 different areas where there could be an issue. It's actually a little bit inefficient to just use this data set alone to go through and check and update your pipe network data. Instead of using that data set, I like to use that to get an idea of the overall problem and then use the flow trace tool to review the data in a little bit more detail. The flow trace tool has all the same options as the continuity tool, but also adds a generate long plots option, which is the one at the bottom of the screen there, the bottom of the list. So I'll turn that on now. And to use this, you basically just have to select the most downstream channel in your pipe network. It will then undertake a flow trace of everything upstream, and it will also create a long profile of all the possible combinations or flow path within that portion of the network. Let me just expand this. You'll see on the right there, there's the paths listed. It's just a matter of flicking through each of those paths after this plot window has been created and reviewing the long sections that are available from that particular outlet. So here we can see something is amiss with this section of the pipe network. We've got a culvert which is substantially bigger than the surrounding culverts that it's connected to. Once I see this, I just click on the select path in workspace button, and it will highlight that select route or that select path for you. Then I can see the error message GIS object there. It's in the screen, it's shown as orange, and also an icon in the long plot will help me locate where the problem is for that particular pipe. And just to further help things along, I would always use the label network button. That would highlight a label for each element along that long section. And I'd also turn on labeling for the GIS objects. And that way I can make sure that the pipe I'm looking at in the GIS object is the right one that I'm worried about in the long section. So once you identify these things, it's a matter of, a little bit further investigation to work out what the right data should be. We'll just do another example. So I'll keep flicking through the different paths. I'm using my mouse to do this, which is a bit slow, or you can just use the down arrow and just flick through them quite quickly. Here's another problem. You can see that pipe is well above the ground level. It's about 7 meters above the ground level. I go through the exact same process. I click on the select path to workspace. That highlights that long section. Go to the location where the error messaging is, and then I can update the feature in that location. The other useful feature of the flow trace is literally just checking for the full, or checking that the full pipe network is connected as you'd expect. What you do here is you click on the most downstream pipe, turn off the long section plot and just click run, and it'll show highlighted the whole connected pipe network to that particular element. And what this is doing is it's basically giving you a way to confirm that everything is snapped together. It could be that the snapping radius that you used in the initial step was too small to pick up a disconnection in the pipe network. And if that's the case, doing this for each outlet to your pipe network will confirm that things are all connected as they should be. In this instance here, both of those sections of the pipe network are meant to be separated. They're not meant to be connected. All right, so you've now gone through and done or you trust the data that's going into your model. The next step would be to enter that data in the model, run the simulation, and look at some results. And I like to focus on a few different summary results to help guide where I need to interrogate my 1D and 2D results more closely to confirm whether the results are correct or not. For this, I'll be looking at 2 different event result data sets. One will be for a small event that roughly matches the expected capacity of the pipe network. Another is for a much larger event, which is orders of magnitude bigger than the expected capacity. So there I've loaded in the pipe capacity summary file, max min flow summary file, and now I'm loading in the dynamic 1D, 2D results. So once again, you'll see I'll open up 2 different result data sets here, one for the small event and one for a large event. Okay, those results are loaded. let's now first focus on the pipe capacity summary result. And I'll be using the event which matches the capacity of the pipe network. First of all, let's just look at what attributes are included in this file. You'll see there's some flow summary results, so percent flow max, percent time when it was full. There's some area summaries, and then there's also some surcharge summaries. For this demonstration, I'll be focusing on a review of the percent full max, but it might also be useful when you're doing these reviews to do a similar analysis for all of the elements where surcharge is being experienced. I won't go into demonstrate that though. You can basically mirror what I'm doing with Pmax, P4 max for surcharging. In the interest of time, there's no need. All right, when I'm looking at that data set, what I like to do is just basically change the symbology of the file to enable me to differentiate between the locations of the model where I've got a high percentage full versus a low percentage. Here, 100 is set to a value of red, transitioning down to a value of 0, which will be blue. Once I've made that change in symbology, I'm basically looking for areas that are an unexpected result. And I'll zoom in on this particular location here, where I can see that the pipe network, I might just try and turn on my pointer. Here we can see the pipe network is red, so it's at full capacity. It drops away before coming back to full capacity again here. So I'll review the results in both of these locations to see if there's something unexpected. I'll use TwoFlow Viewer for this. To start with, we'll look at the time series results. Switch off the summary file, load in the actual 1D results. I'll select flow as the result type. And then I just need to select particular elements in the pipe network where I'd like to review the results. So I need to select that file first. There we go. So you can see the flow through that element and the flow through the one downstream. They actually don't change all that much, which doesn't really correlate or compare well to the capacity map result. That being the case, the cross-section long profile tool is quite useful. If I use it, I can select the same pipe elements and then simply plot the culvert and pipes output type, and it will display the pipe network for me through that area. And here you can see that the pipe network or the pipe size has increased as you're moving downstream. So that explains why capacity has changed. Probably no need to further look at that location for the results. Let's look downstream though. There's something a bit more interesting happening down here. If I select those two pipes, you can see that the flow drops off dramatically for the downstream pipe. Now, if I zoom in to look at the 2D results at the same time as the 1D, I'll just look at the unit flow results. We'll start to see what's happening above ground at the same time as what's happening below ground. Now we're finally seeing some flow. You can see a concentration of the flow down many of the roadways, which are underneath the pipe network itself. If you look at these results, you can see there's very little flow in the roadway upstream of that area where the flow changes significantly in the pipe network. And then there's a concentration of flow above ground below it. So that suggests to me that there is surcharging in that location. And if I then click on the pit inlets at that particular junction, that then displays the 1D results for those. And on the left, you can see the orange line and the red line are both going negative. So we're seeing that there's surcharging in that particular location. We can also look at the long section, long profile plot again to see what is causing that. Once again, I'll select two pipes and the long section tool will plot between the two. So I just need to update the plot window here. There we go. So we can see the whole pipe length there. We can see the pipe size decreases where we're experiencing the surcharging. The other lines and points on that graph on the left represent the results. So the red line is the maximum water level for the entire simulation. It's obvious there where we're seeing the surcharging. And the blue line is the instantaneous one for whatever time slice I've selected. The green dots are the pit ground level. All right, so imagine I've gone through the pipe network and done enough of a review for the moderately sized event. Now I usually switch over to looking at the same result file type for a large event, one which is much, much bigger than the capacity of the pipe network. And here I like to just sort the data based on the P full max, percent full, or the maximum percent full for the whole simulation, and identify all of the objects which have a small number. These are pipes that are not flowing to capacity, and I'm just looking into each of those ones individually to assess whether that result is valid or not. The other summary file I look at is the max min flow summary file, so the 1D mmqp.shape file. I've already thematically mapped this one because I've shown you how to do that in the previous slides. Let's first of all look at what the table looks like. If we look at this, you can see for every single pipe element, there is different flow statistics, or some statistics, flow summaries, different time summaries. Yeah, so you can use this data in a variety of ways to identify those areas where the results aren't what you'd expect. So if we look at this data, the areas that are red are high flow, transitioning down to blue, which are low flow. And here's one location where things look a bit weird. We've got the flow transitioning from green up to yellow, orange to red, and then dropping away through here down to green and yellow before going back to red. So once I've identified this as a potential area of issue, I go back to using the two-flow viewer and interrogating the 1D, 2D results again. And it's exactly the same process. I would click on the result or the actual element of interest and plot up the flow results. So you can get a sense of what's happening here. That's the upstream pipe. There's the downstream pipe. It's going from 2 meters cubic per second down to almost zero. And if I click on the pit inlet, you can see that all the water is surcharging there because we've got that negative flow out of that pit. It's the green line in the graph. Once again, we can look at the 2D results at the same time. I'll just skip straight to the peak here at 40 minutes. And there you can see that at the pit inlet, we're seeing quite a concentration of flow coming out in that location. So it's the source of quite a bit of the flooding above ground. And yes, same as last time, we can also look at the long section. That can always also tell us some useful information. Here I'll click somewhere upstream, somewhere downstream, and I'll just plot the culvert just to see if there's any geometry issues. If there's not, then I'd look at other things such as the inverts on the pit versus the inverts on the pipe network itself. In this instance, you can see that the pipe has gone from something that's around 1.2 meters down to 0.2 meters. So it'd be worth further investigation to see if that culvert that's at 0.2 meter diameter is real or not. Okay, when it comes to urban modelling, if you can calibrate, please do, because that will also identify areas where your model result isn't reflecting reality. That being said, it's actually, I'd say, quite rare to get calibration data for urban events or these urban stormwater events. That doesn't mean that you can't do comparisons against what's happening on the ground and what's happening in your model. And I've often found that most councils, cities, would maintain a register of their stormwater problems. Like it's, I guess, like a hotspot register. It's a very useful exercise to take that register and compare the hotspots in that to your model result. And if you're seeing that they don't correlate, then it's a matter of further investigation to work out why that's the case. Yeah, so look, in summary, for when it comes to pipe modelling quality control, for pipe network modelling, I guess with any modelling, the quality of your input data influences the quality of your outputs. So there's a lot of value in checking your data before your modeling, and also for your early simulations before you lock in a final model configuration. I'll leave it there. It looks like there's lots of, there's a few questions there. So we'll close it off. We'll open up to question and answer time, where I guess I'll pass it over to Phil.
Yep,
Yeah,
over to you,
thanks,
Phil. All over to you, Phil. That'd be great. Moderate
Thanks,
this.
thanks,
Great.
Trevor. Thanks, Chris, and Bill as well for those presentations. I'll run through some of the most upvoted. Then the first question that I'll go through to Bill is one that Bill has said he'd like to answer. Can you provide comment or guidance on modelling techniques to achieve the correct depth at the surface to ensure correct inlet capture with the pit rating curves versus depth? Can you comment on the role of unlimited inlet pits and cases where these are applicable? Often large-scale council-wide studies don't include all pit data like the small data, and the most upstream pits require a greater inlet to allow more flow into than the actual pit to represent the upstream network. Bill, that's one you flagged you'd like to answer, so that's straight over to you, mate.
Yeah, thanks, David. Great question or questions. These days, if you're using subgroup sampling or the mesh refinement options such as Quadtree that we now have in 2Flow, you'll get a much better representation of the depth at the entrance to these pits. So that is strongly recommended. If you're using an older version of 2Flow, we don't have that feature. There is a road crossfall feature that people often turn on, and what that does is it just increases the depth at the pit using that crossfall slope, and that gives you improved capture. But certainly for new models, subgroup sampling will provide, and provided your DEM is sufficiently accurate, that will give you a much better representation of your depth at your inlets. In terms of, it's a challenging one when you have lots of the network which is upstream. I mean, a little bit depends. If you've got a significant sort of pipe catchment system, you may need to try and capture that, and possibly through a separate sort of hydrology model. But if you're using direct rainfall, so it's a real challenge if you don't have those pipes, and they do contribute to the underground flow. I mean, I think you're just going to be very careful of your results down to where the point of starting to model your pipe network. And it is a challenge. Otherwise, I think one of the other questions.
Actually, Bill, before we move on, can I just add something?
Go for it, Chris. Yeah.
Over the Christmas break, whilst the support line was a little bit quiet, one of my tasks was develop an example data set that modelers can use, and so create in the order of 140 models that demonstrate all the features. And one that's included in that data set is one where we have virtual pipes connected to the pipe network, which is a really nice feature. So you can have your pipe network where the question mentions everything greater than 450 mil. Your pipe network might include everything that's greater than 450 mil. And then for all your collection points, you could use virtual pipes to direct water instantaneously to that pipe network. So keep an eye out for that. Bill's due to review my documentation for it this week. It'll probably go live maybe next week or the week after. But that's a really nice function tool.
Yeah, thanks, Chris, for reminding me. I have to say, these guys do all the modelling and all the hard work these days. I just have to try and keep them under control, so I tend to forget some of the features. But that virtual pipe feature, which Greg and I put in years ago, is very powerful actually for pushing that water, because you can connect that virtual pipe system to the start of your actual pipe system. The thing you just have to keep in mind is that there's no travel time. So as water is captured in the pits, that water is taken into the pits and it disappears at the outlet, which you specify, which would be the start of your 450 pipe system, and it goes into the pipe system. So, but it would capture that much. That would be your best option particularly if you're doing direct rainfall modelling.
I will give the exact model number so Dave can look it up. It'll be model example model 15, number 8. Yeah,
or Dave, if you email support@2flow.com,
actually email support at 2flow.
Yeah, they'll direct you to that one or send it to you.
And while we're on pits and pit losses, another one that's come through is losses at pits are complex and vary depending on the depth of flow over the inlet. When two-flow modelling a pit as an R-type pit, is it possible to pick those loss values, or is that why we generally recommend the Q-type pits? Bill, do you want to have a comment on why Q-type pits are the...
Yeah, a strong recommendation is to use Q pits, provided you've got curves for those pits. Yeah, I mean, that's always the preferred way. The R pit was sort of precursor to the Q one, and it works okay, but yeah, I would strongly recommend trying to use the Q pits if you can. Yeah, I'm not sure anyone wants to add anything to that one.
No, I think that's pretty good for me. Can you use a drainage spatial data stored in an SQLite database rather than a native GIS? I'm picking on some of them that have been answered, but are actually some of the most upvoted questions. So, Bill, I think you answered that one as well.
And did I correct me if I go wrong, because you guys are the brains behind all that.
So for the two-flow 2022 release, we are moving towards supporting the spatial light databasing as well as the GIS, the shapefile and the tab file format. So GeoPackage will be supported as well. So that probably answers that one. I think we are starting to run out of time. We might maybe throw one more in there, which is, can we use the same equations? This was specifically answered when the manhole was on in open channel flow for energy loss calculations, or are they specific to manholes?
Well, you can. It just manholes have a K value for manhole will be picking up all the complexities of the manhole, but typically values related around bend losses and so forth would potentially be applicable. Yeah, I mean, open channel flow has, particularly if you're doing it in 2D, a lot of those expansion losses will be modelled. So something just bear in mind is if your open channel flows in 1D, you won't necessarily pick up very well your expansion losses if they're quite acute. If you're going from, but in 2D, you will actually pick up losses around bends and so forth, as long as you're using a good scheme with inertia and turbulence in the scheme and a second order solution. So it's less of an issue in open channel flow, particularly if you're modeling with a higher end scheme in 2D. But we have found in the past something like very severe bend, you do have to put in additional energy losses, and this is based on calibration, particularly of the Brisbane River system, where we had very good data. So sometimes a 2D scheme isn't capturing all the energy losses. So and you really don't probably want to go to a 3D scheme for a lot of this modelling. So 2D will give you that much better representation. But if in 1D, yeah, just be mindful of that.
Excellent. And that takes us to almost 10 minutes over time. So unless there was any other questions that Chris or Bill you'd seen on the line that you wanted to answer, I probably would wrap it up there and say thanks to both Chris and Bill for presenting and to AWS for hosting.
Been fantastic, guys. Absolute pleasure. Let's do this again on, when are we going to do it again? Next webinar for two-flow is 16th of March, 3D Coast Modelling 101. And I don't know who's going to be doing that, but I can see
Mitch. None of us.
Mitch, right. That's been good. Thank you. That's been absolutely fantastic. We've really, really appreciated the hour, and I've learned heaps. I didn't know there was so much intelligence. AI, no, that's wrong. I didn't mean it like that. I meant the built-in software intelligence sitting behind this, so you can interrogate the actual models, see where the problems are.
Sorry, I'm going to send you your exam questions in a second.
I've studied up, Bill, and I can do Manning's equation. Let me get it right: volume, area, and slope. Good.
Yeah, you're doing well.
I'm in. Hey, everybody, don't forget. There's a recording coming to you, and that'll be emailed to you, and you can go to the website, YouTube channel, give it to your friends and watch it together. Secondly, certificate of attendance is coming to you also. And thirdly, the big one is scan that QR code there, or the pop-up survey will come up, and we'd love to have your thoughts. It'll really help us shape it. Yeah, thanks everybody. I can see your chat line is going mad with great presentation, good presentation. Thank you. Yep, that's terrific. You can see it, presenters and You can see the chat line going mad there.
And Trevor, I'll just
yeah.
add, just one final thing is a Q&A. We'll scan through those remaining questions and send some answers.
Oh, thanks very much. That's fantastic. People, presenters send that out to people. That's really good. That would be excellent. So you can see on the screen there, on-demand courses, webinars and live courses. The Australian Water School has, I don't know who can beat it, but it'll be pretty hard to beat. You don't have to get on a plane, you don't have to do anything. Just study up the upcoming live courses, webinars and on-demand courses. It's brilliant. Thank you, Australian Water School, and thank you to 4 presenters today: Bill Syme, Chris Huxley, Phil Ryan, Greg Collicutt, spread across Australia. Where do you live, Phil? Southern Cross. Iconic name in Australia, everybody. We'll get that right.
Yeah, down in Victoria. Yeah.
I've got it right. Thanks everybody for joining us today. It's been a terrific, engaging discussion, and we hope to see you again soon. Thanks very much, everybody.
Thanks, Trevor.
Excellent.
Bye for now.
Thanks, everyone.
Thank you, everyone.
Bye. Bye.
Thanks for watching. Subscribe by clicking the link below and click on the notification bell to stay up to date with new releases. For the latest in significant, innovative and critical advances in water science, technology and management, subscribe now. To build your skills, enhance your technical knowledge and learn from leading experts in water, visit theaustralianwaterschool.com.au and discover our online training courses, both live and on demand.